Let's begin with the definition. This is of pointwise convergence. Pointwise convergence. Let Fn from S to R be a sequence of functions. We say Fn converges to the function f from S to R pointwise if for each x in S, Fn x converges to f of x. Okay. In the last module, we have already seen an example of such convergence. We saw that this function x bar n converges to the function that is 0 if x is in close 0 open 1 and 1 if x is equal to 1. We already saw this. So we know that this pointwise convergence of a sequence of functions is not a guarantee that the limit function will also be continuous, even if you start with the nicest of nice functions x bar n. This need not happen. So what we are going to now do is to reverse engineer and try to find out some appropriate condition that will guarantee that the limit function is continuous. To do that, let's try to see what goes wrong if we naively try to prove that the limit function is continuous. So what we are going to do is we are going to consider Fn converging to f pointwise. We have pointwise convergence Fn converging to f. We are going to take x in S to be a limit point and try to show that the limit function f is actually going to be continuous at x and fail miserably. At the isolated points of the set S, f is anyway continuous, so I don't care about those points. All the issues will come at the limit points. Okay, so what we are going to do is the following. What we have to do is fix epsilon greater than 0. We have to show that we can find delta greater than 0 such that if mod x minus y is less than delta and y is coming from the set S, mod fx minus fy is less than epsilon. This is what we have to do. Okay, now of course I must mention fn's are continuous. These functions fn are continuous. Otherwise, this whole enterprise is doomed to fail right from the beginning. Okay, so now that we want to show mod fx minus fy is less than epsilon and the only data we are given is about the continuity of the functions fn and the fact that fn converges to f, the natural thing to do is to play the oldest trick in the book and introduce fn's by adding and subtracting. So what we can do is we can add and subtract fn of x. Okay, then we can add and subtract fn of y. And then let's expand this out by triangle inequality. We will get less than or equal to modulus of fx minus fnx plus modulus fnx minus f1y plus modulus of fny minus f of y. Okay. Now this splitting up the term to get 3 terms in this manner repeatedly arises in analysis. So be very careful and try to understand what exactly is going on. Okay. Now if you look at these terms carefully and ponder for a few minutes, you might be deluded into thinking that actually this professor is saying nonsense. The limit function f is certainly continuous. Why? Because think about this. This f of x minus fn of x can be made less than epsilon by 3 simply because fn of x is converging to fx. The middle term fnx minus fny can be made less than epsilon by 3 by choosing delta appropriately, right? Because fn's are continuous, you can choose a delta so that mod fnx minus fny is less than epsilon by 3. And of course, the third term can be made less than epsilon by 3 for exactly the same reason. Fny converges to f of y. So you would think that it is certainly possible to make mod fx minus fy less than epsilon by choosing delta appropriately, but not so. Not so quick. Let's see what happens. First of all, we can choose capital N so large that mod fx minus fnx, of course this should be capital N, is less than epsilon by 3. We can do this simply because the sequence fn converges to the point f of x. We can choose capital N so large that fx minus fnx is less than epsilon by 3. So the first term we can handle. Now what about the middle term? Well, we can choose delta greater than 0 such that mod fnx minus, of course this should be capital N again, fny is less than epsilon by 3 whenever mod x minus y is less than delta and y comes from the set S. We can do this. So what we have done is we have controlled this first term by controlling capital N, small n, and setting it to be a large enough number capital N. Then we are controlling this second by the continuity of f capital N. Now what about the third term? The third term is now we have to control f capital N y minus f of y. Now here is where the issue lies. Y could be any point such that mod x minus y is less than delta and y in S. And the issue arises because just by ensuring that modulus of fx minus fnx is less than epsilon by 3 does not give us any control on modulus of fny minus fy. We might have to bump up this capital N. We have no control over y. So depending on the choice of y, which is now contained in this, which is delta close to x, we have to choose capital N possibly higher depending on the choice of y. So we cannot make the above term less than capital N, less than epsilon by 3 without adjusting capital N. And this adjustment would depend on the choice of y. In other words, there is no uniform way to do this. There is no uniform way to do this. Okay, so this discussion motivates the following definition. The definition is just modeled so as to make the above flawed proof not flawed. So let Fn from S to R converge pointwise to the function f. From S to R. We say Fn converges to f uniformly. So uniform convergence is stronger than pointwise convergence if for each epsilon greater than 0 we can find capital N in N such that if N is greater than capital N, then modulus fnx minus fx is less than epsilon for all x in S. The previous definition of pointwise convergence merely said that fnx converges to f of x. Therefore, the choice of n would crucially depend on the choice of x. Whereas in this definition of uniform convergence, so this is the definition of uniform convergence, the choice of n does not depend on the choice of the point x. You can find a uniform n that works simultaneously for all the points x in S. Okay, so let's immediately prove a theorem, and this theorem's proof should be fairly clear. If Fn from S to R are continuous and Fn converges to F uniformly, of course F is from S to R, then F is continuous. Okay, let's see the proof. Most of the work is done. Let's see the proof. Fix x in S to be a limit point, and okay, and fix epsilon greater than 0. Fix epsilon greater than 0. Again, we can write for y in S, we can write mod mod f of x minus f of y is less than or equal to, as usual, exactly as we did in the preceding discussion, minus f1 x plus fn x minus f1 y plus fn y minus f of y, and this just becomes modulus of fx minus fn x plus modulus of fn x minus f1 y plus modulus of fn y minus f of y. Now here is the crucial fact. We can find capital N such that both the first and third term are simultaneously less than epsilon by 3. Okay, it doesn't matter, no matter what points x and y you choose in the set S, you can always find a capital N such that mod fx minus fn x is less than epsilon by 3, mod fn y minus fy is less than epsilon by 3. So these first and third terms can be made less than epsilon by 3 simultaneously. It doesn't matter where x and y are. Okay, now choose delta greater than 0 such that the middle term 2 is less than epsilon by 3 whenever mod x minus y is less than delta and y is coming from S. Okay, so putting all this together we see that modulus of f of x minus f of y is less than epsilon if mod x minus y is less than delta and y is coming from S. Hence, f is continuous. Okay, so the definition of uniform convergence was built precisely to make this argument work. Now in the next few modules, we will explore certain properties of uniform convergence, how it behaves, how uniformly convergent sequence of functions behave under differentiation, under integration, and so on. Then we will apply these results to power series. It will turn out that any power series that converges in a particular interval will do so uniformly with a slight twist. We will see more about this in the future modules. This is a course on real analysis, and you have just watched the module on uniform convergence and continuity of limits.